that the university gives me, so I'm doing two different recordings. And so first of all, whoops, let's see, I could turn off my speaker too, because my mic's on, that's what matters. Excuse me. So the one thing last week is, yet again, I've learned how to screw things up that I had not realized that that the tracks are the two tracks that when you face this wall go from gate 0 as at 220, and then the other tracks have gate 0 at well, I got this thing on my screen here, and I'm trying to get this. It's blocking. How do I get rid of this? Ugh, Harry's personal. I have this black box on my screen, and I don't know how to. Ah, there it finally disappeared. Okay. Okay. Now, anyways, at the last minute, we found this business. We've also faced up, if you recall, from when we did the tilted track, about having gate 0. They're reversed in a way, depending on which direction, right? So I thought I'd ask people to send me their data, and I didn't, but I realized that it's not a big deal. If, for example, now we look at the table I have there and the graph, you'll see that this is what would happen if you had you started from gate 0 well, in this case, gate 5, right, at 70, you would see that by the time the gate 0 would end up with the longest time, no, the one, well, in any event, no matter what's going to happen, you're going to get a blue dots that are going to be in a nominal straight line. They may have a negative slope, they may have a positive slope. You may end up with negative velocity, but you actually don't have to do any kludging. So I'm just going to put this one back to the way it was. Remember, we talked about maybe adding a -1. It turns out I feel pretty confident. Of course, I'd be more confident if I had real data. This is data, I forget where it came from. So I did the standard business. I have the gate position, and I have the time I read off from each one. And then I get the T average of the two previous times. That's the middle of our bin. And I got my delta T. Right, this is all ho-hum, another delta x, and remember we sort of talked about putting a -1 there. It's not necessarily, just plot it. If you've already done it with a -1, that's okay. As long as you use the -1 there for every single one, it's fine. So at the end of the day, we have our 4 or 5 different runs. In this case, I have 4 different runs, and I supplied you with the fit parameters. So all you had to do is type in your data, and everything else populated, and then you just had to run the solver on it to get the optimal fit. And by the way, I remember now why we want the standard deviation of the sample. And notice we're doing it on the residuals. And this is part of, let's make believe, you see our blue dots on the plot there. So make believe you're sitting on the paper and you're looking along the red line. And you would see those blue dots, sort of like a little histogram, right? And so if we take the standard deviation of the residuals, it's basically taking that histogram and putting it at 0, the average value of 0, and then we look at the standard deviation of them, and then divide by the square root of the number, and that's basically the plus minus on those. Excuse me. That's a way of saying the plus minus on the slope. It's not the best way, but it's one that passes the LOL test. So you may have deleted it in the spreadsheet I provided you had it. So just so you see it again, it's a basic command. And once you do it, if you don't have it anymore, you just can enter it in one. And let's see, I'll clear this first, and I'll redo it. Oh, what's going on? Oh, right. Backspace. Equals dev dot s, and then open the parentheses, and then you do the residuals. And then I used a fancy one here. I divided that by the square root of n, but I used this function called count. And it's useful if I have a real large number of points. And we saw that in the circadian rhythm. So you divide by the square root of the number of things that's in that you got the standard deviation of. And again, if you don't have those anymore, you can simply then copy this. There's no dollar signs, so you can just now go here and paste it, and it's there, and you just go down the line. And we're going to use that as the standard error of our slope determination. I'm going to show you the hardcore way of getting the error on the slope, but we don't want to do that 4 or 5 times because it's a little tedious. I haven't learned how to automate it yet, but I'm going to show you that, and then of course I'm going to show you the R-squared test. Okay, so you may already have it there. Now, remember we had this summary table here. It's also known as a concatenation. So, and mostly you have that set up already. Let me just, so we can see things. So we see that that's the one slope, that's what, M5. And then the other slope, in this case, M21. And then the plus minus is, oh, where'd it go? There it is. The standard error there, I12. You can't do the pull down box here, but what you can do, now here's a trick in Excel. When I copy pasted all these blocks on the left side, I make sure that they have the same number of blank spaces between each one. And the reason I do that is when I need to do something like where I can't use my pull down box, notice that that's M6, M21, they're each 15 boxes apart. So right away I know this is M6. Oh yeah, notice I used the absolute. So this is why it doesn't matter if you get negative or positive. If you think about it, you should get positive, but we're not going to go and do anything fancy. We're just going to say absolute value. So whether or not you got a positive slope or a negative slope, as long as that each one of those blocks on the left, you got the slope in the same exact way, so they're going to all be negative or they're going to all be positive, you're fine. And as I was saying, M6, right, so I know they're 15 apart, so I just have to go equals absolute M21. Or I could just drag them, like to save even some more typing, I drag them. And then I know this one has to be 21. Then 21 plus 15 is 36. And then 36 plus 15 is 51. Or another trick you could do is here. Well, it's not going to work every time, never mind. But also notice this one is I12. Then it should be I27, always 15 apart. And the same thing with the masses. Although in principle you have those entered already, but I just wanted to share with you some of the things I've learned over the years. Whenever you copy blocks, repetitive blocks, always make sure that you space them equally. Okay, then I've got my masses, then I calculate my 1 over m plus m, right? This part we looked at a little bit last time. And then I can make my mg, which is, in this case, since we decided to leave everything in centimeters, it's 980. And it looks like absolute, but it's AB5, which is the mass, that little m. And then I remind you that one of these two, I don't remember, we're doing differently than the manual, because we're always going to put, since we're measuring A, that's always going to be on the y-axis. And we know that A equals F over M, which is, and unfortunately, we have, well, let's say mass, just to not to mix up. And so for us, that's going to be mg divided by little m plus capital M, always. So in our case, we're doing constant mass and constant force. So with constant mass, that means that our slope is going to be that mass. And in this case, 1 over it. And mg is going to be our x-axis. So in constant mass, this is the slope. And then when we do constant force, we use the same exact equation. So this is constant mass, just so I'll put it on the constant force sheet, but I want to just finish the thought. When we do constant force, then it becomes mg becomes the slope, and 1 over little m plus big M becomes the x-axis. Okay, so in both cases we need 1 over m plus m. And in both cases we need mg, so it's slightly different than the lab manual. So then our fit equation, if it's going to, oh, that's right, to go over here, is now, there's our slope and our y-intercept. And then, as I said, the x-axis in this case is mg, and that's the red highlighted box. And then we go down, then this one you can drag. Somehow that looks like something changed there. Yep. I always make a point of when I highlight something like this for you, you should make a habit, then you hit escape just in case, because if you click somewhere else, you notice that gets inserted into the formula. So I just hit the undo button. So now I've got my formula set up, and I added in. Now, of course, it's better to graph it first, but I added in 0 and this 9,000 because I noticed that my largest value of, or 90,000, my largest value was 83,000. So I want to make, I know that Excel is going to pick a round number like 8,000 or 85,000, and it's nice to have the fit line go across the whole graph. I think I've mentioned that in the past, but of course, it could be that it's from a different class. I'm mixing you up with a different class. Excuse me. And now we have the standard residuals, residuals squared. I have put the error bars on this. They're hard to see. And that is the plus or minus over here. And if I yes, so I go over here and I want y error bars and specify the value, and there we go over here. They happen to be small. And I think you guys too. You guys are, from what I've seen, you guys are really good at taking data. I'm glad. I'm proud of you. It's ironic that you guys in the pre-health classes, you're careful, you do what I ask you to do, and the engineering kids in the higher level, they're so indifferent. I don't understand, right? I mean, the stuff we do for them is so much more applicable to their careers. But anyways, let's see. So we've got our graph, and then you can do your fit. And now, I think I've mentioned the chi-square. So the chi-square is simply taking the residual square and dividing it by the error bar squared. Can you see that on your screens? Should anybody need me to zoom it in or anything? No. Guys, you guys are a pleasure. I'm sorry I let you down this week. So that's all. And the reason number one reason you do it is that if there's a point that's lying far away from the fit line, our simple rules say we need to address that point. We need to respect it. But if it has a large error bar, we sort of know that we don't have to pay too much attention to it. When we're fitting by hand, when we were adjusting the slope by hand and looking at the residual squared, you can sort of do that. In fact, you could do it with the chi-square. What the chi-square does, if you think about it for a minute, and it doesn't apply in this case because our error bars are all the same, but there's another reason to use it I'll get to in a minute. If you think about it for a minute, that our figure of merit is the sum of the residual squared. And as such, it treats each point equally. If I divide each point by its error bar, and remember, I'm dividing it, right? So the large error bar makes that value for that point smaller. So when it comes to summing them, it has less effect on the sum. And this is the way you tell the computer to pay less attention to the points with large error bars. And again, in this case, it's not that relevant. For us, though, we are going to learn how to find the plus or minus slope. And the way that's done is using the chi-square. So I may have drawn something like this before. Come on. So if I look at a plot and now it's the chi-squared, which is basically the same as the residual squared. And in our case, there would be two of these graphs, one for the slope, one for the y-intercept. But we're interested in the error in the slope, because for us, that's what counts. And just like the residual squared, the chi-square is a parabola. And remember, that's what we like, because that way we know that we can find this minimum point, right? And so the slope, the best slope is at chi min, sum chi-square min. So I'll just instead of writing all that out, we already know the y-axis is the sigma. This is the min of the sigma chi-square, so that's our best fit. So if we want to know what is the plus minus on it, it's very heavy math, believe it or not, but the rule is, it's not just arbitrary. We say whatever is the min, we say min plus, well, I don't want it, it's going to get in my way. Let's put it somewhere else, and let's try a different color. We make a point here, which is min plus 1. Make sure you give yourself little notes in your logbook, and of course you can jazz them up later. And then if I go across that point, of course, now because of the cup shape, we have now two crossing points. So when I drop these down, this delta slope, and if I divide it by 2, that's my plus minus. That equals my plus minus slope. And if you think about it for a minute, when you do it with a ruler, they tell you what's the line you can fit that basically passes through almost all the points, and what's the minimum. It's just about the same, because you're also supposed to pay attention to the error bars when you use a paper and pencil. Or maybe you don't know that, right? I keep forgetting, you guys. I had to do this when I was in like middle school, right, with a paper and pen. But you guys don't, right? But also I don't see why sometimes I ask students to do it, sometimes not, but at week 7, we shouldn't be using paper and pencil graphs anymore we're, in 2022. But you need to know this, right? And this, I learned this in graduate school also, at this part that I just showed you. So what we're gonna do, is we're gonna call these two red points extreme points. And then you see that over here, I've created with my fit parameter table. So those are my two extremes. Because what we're going to do is we're going to ask solver to, instead of finding the minimum chi-square, we're going to ask it to find a sum of chi-square. We're going to ask it to find a particular one. In fact, notice that we have our best fit value here now. Oh, it's a new drawing tablet. I got to get used to the quirks. My drawing tablet, I've had it since COVID days. It gave up the ghost the other day. Hope I can fix it. So anyways, here is the sum, right? So this is a little tedious. I haven't been able to figure out how to have Excel do this completely automatically. So we're going to copy that best fit value. And then we're going to, over here, and notice I labeled above it sigma chi-squared plus 1. I'm going to paste, but I'm going to paste value. So you either have this little clipboard with the numbers, or if you see paste special, you pick values. Now notice it's this big long number, and we're going to even get a little kludgier. We're going to add a couple decimal places. And then, of course, we need to make it, nicely enough, adding 1 is not so hard, right? So this is just going to become 2.8. Okay. Now we go back for the solver, data tab, solver. Now we got to make a couple small changes. Now we say we want to go to a particular value. You can see I was doing it. Okay, so I used only 4 decimal places, but I'll use what's there. You can't copy paste. And notice it would be real convenient if it had one of these arrow thingies, right? And then I just want to make sure it's the right, sigma chi-square. And now, though, we only want to vary the slope. We don't want to vary the y-intercept, because we just want to find the plus minus slope. Okay, see? Oh, wait a minute. Now, I even tried typing in a cell number too, it wouldn't work. Okay, so now I hit solve. And let's just see that it didn't do something absolutely crazy. No. Okay, now, if you think about it for a minute, it could have given, it's now given me what? Oh, it's given me something that was lower than the previous number, it looks like. And so it could have given me something that's higher because there's two different ones, right? So that's why I said extreme and not the plus slope. So now what we do is we take this number and we copy it and again paste as numbers only. Notice now the plus minus is now 0 because now the two of these are equal. And I suppose what we could have done was, oh, we do know the best. No, we don't remember. We could have copy pasted the best fit slope, right? Because then we wouldn't have to rerun solver. But me, I just figure I'll rerun solver. Maybe I'll find that something is wrong. But in principle, I could have just copy pasted the best fit slope. And also now we have to remember we want to do the slope and the y-intercept. And we hit solve, and let's just, looks good. Okay, now, oh, nothing happened. What did I do? Oh, I know what. Remember, I forgot to say minimize. And there it is. So in this case, what we found is the value of one of the extremes. We didn't find the delta slope. And so that means that we've either found the one above or below it, so we take the difference between these two numbers, and that becomes our plus minus slope. And because it could end up being a negative number, I just used absolute. And I made a percent, what's the relative error? So the plus minus divided by the value and times 100. And this is just because I wanted to know. Also, what happens is now we don't have an accepted, remember we discussed this last week, we don't have an accepted value to compare it to, right? But already we can say, hey, look, we have a 0.64% relative error. So even if our data, if something's wrong, the data we took is pretty darn good, right? The spread of data points around the red line is really, really good. I'm a little unhappy that the error bars are not covering the red line. And that's again mostly because we can't quantify them, and that's why we use the standard deviation as the error on our accelerations in the little plots. Now, there's two other ways of judging what's going on here. So the first one is called the sum of the chi-squared per number of degrees of freedom. And in our case, we have two fit parameters. And so we have the number of data points is 1, 2, 3, 4, 5. And we subtract 2. That gets us 3. And in fact, I have a number of degree of freedom here as only 2, and it's actually 3. Now, when you get a value of 1 or abouts, you're extremely happy. If you get a value up to about 10, you're still reasonably happy. If you have a value less than 1, then what the rule of thumb is you have some unknown systematic error that you didn't account for. Now, this is telling me that my data must be artificially generated, because I don't think you guys are going to get such a low number. right? But if you get a chi-squared, that's the gold standard. Chi-squared per degree of freedom is equal to 1. That means that your equation, the fit equation, and the parameters you chose to fit are good, they match. And for us, well, one of the things we needed to demonstrate was that Newton's law is linear in the variables, right? So we did use a linear fit, and we have a really good chi-squared per degree of freedom. But the other test is called the R-squared. And so the R-squared is this one here. So you should get that down somewhere. And it's, there's a Wikipedia article, in fact, which I went to remind myself of how to do this. And yeah, so I'll get back to this in a minute. The numerator here is the sum of the residuals squared, which we already have. And the denominator is this odd quantity here, because normally this thing inside the sigma symbol, the in parentheses squared, you might recognize that as part of the standard deviation, right? And that in fact is called the variance. But you normally don't do that because in this case, we don't expect that the average value of the data points is a meaningful number, right? Because we don't expect it to be the same each time. When you measure the length of something, you expect to get the same number each time, right? And so I looked here, and I can kind of see it because so if you look on the left side, so what's going on there is that if I had a slope of 0, no, let's see, SS total represents, right, I get it. So SS 0 kind of represents if we expected these values to all be the same, so that would mean that there's no functional relationship. Now I finally got it. So this, and I think this, you may have to face up to this someday, right? So the SS total is telling us that if that number is small, that would mean that the data the X and Y axes have no correlation. And that's the equivalent of the straight flat line, right? That means if I vary the X axis, nothing happens to the Y axis, no correlation. In our case, we have a correlation, and so we have deviation from that line. And then you notice we minimize the residual squared. So you'll notice then, in this case, is this only for a linear regression? No, it's for any function. But in this case, you see that because the straight line fits the data pretty well, the SS of the residuals is pretty small. And in fact, any fit you do. Now, what would happen is if we used a different function, the sum of the residuals would never get to be very small. And so if you think about it for a minute, the red one is like zero correlation, and the blue one represents the degree of correlation to the fit function you choose. So if you chose the right fit function, the blue divided by the red will tend to go to 0. And for some reason, they decided to define it as 1 minus. I think it's folded up inside the math, and I don't want to get involved because I barely understand it. I mean, I agree with it, I follow it, but I couldn't explain it to save my life. All I know is this is a standard way of doing it, and now that you look at these two plots here, you understand how it, in a way, hand-wavingly, you understand. So when we needed to construct here, the variance, so here it is. And can everybody read that? If you like, I can zoom in on it. So I just said the data point, so Z5 minus the average of all the data points. Z5 through Z8, notice the dollar signs. And again, I can zoom in if you like. It looks like everybody's down with it. And then once we get it typed in, then we can use the drag handle. And just as that plot in Wikipedia suggested, the points in the middle are smaller and the guys at the extremes are bigger. And then I already have the sum of the residual squared. Oh, and then I sum them. You have to sum them. Excuse me. Excuse me. Ate my lunch too fast. My dad would always, he can come, he go, oh, you enjoying it the second time? He could be so rude. And then once I have that sum, I already have the sum of the residual squared, and so I just construct the final equation. 1 minus the residual squared divided by the sum of the, I forget exactly what SS tot stands for. So now when you go to a talk, like if you're going to be a doctor someday, or you're a biological researcher, or you go into class to become an LPN, and somebody gives a talk and they say, well, we took this data, we controlled it, we got an R squared value of this, now you know what it means. And that makes you better able to ask questions, or if you present and somebody asks you about your work, you know how to defend yourself now, right? That's why I decided to go into this for this 1100 level class, because I think that it's useful, and if you use a spreadsheet, it's not hard. If you use a trend line, the trend line will give you the R squared value. In fact, let's give that a try. I don't want you guys to use trend lines, but what I would say is that in your professional lives, it's a common thing, and it's fine. But I would always caution you that anytime you use Excel, you should build up your spreadsheet and the equations and test them. And now we know how to do fit lines, and we know how to do R squareds, then it's okay to use them. For now, though, I will harass you if you use them. And so one thing we want to add now is display the equation on the chart and display the fit line, the R squared value, and let's compare it to what we got. So they got us, yeah. So I'd have to format this number, but we got the slope right. And look at that, holy shit, got the R squared value exactly right too. Well, it should be, right? We used the official definition after all, right? I don't know. I'm always pleased when things work out the way they're supposed to. No, but this is fairly complicated, right? I mean, it's not like, certain things in life. But in this case, it's super important. Excel is very powerful, but it has the limitation where you have to enter formulas on one line, right? That's partly why I create the residuals and residual squared, et cetera, in separate steps. And that means that any given time, I don't have to type in a whole lot. That's another insider tip, right? And it also makes it easier to debug. Because I've set up these big spreadsheets where I've like written out the formula that I think I need with all the parentheses and typed it all in, and then later on there's a problem, it's not producing what I expect, and it takes forever to go and debug it. So it's always better to build up a spreadsheet in pieces. And then also notice how we built up the spreadsheet for the tilted track, and we just copy pasted the parts into the new spreadsheet, right? That's another power for this. Okay, So what I'm gonna see is the constant force is exactly the same thing. And so I'm gonna post this recording, and I'm gonna ask you guys to do this yourselves. So I won't have this final analysis for this one due until after next week, right? So we can look at it one more time. Because I can do it for you again, but you'll learn it better if you do it yourself, right? So you already have now the constant mass done, and you'll have the recording. And so now you can go back here and try to finish up your constant force. And we'll compare notes on it next week. Okay? All right, so I'm going to stop this